Next slide. So the scattering now, when the light hits the particle, it can be absorbed and it can be scattered. It's the scattered one that we have interest in. So if it hits a particle, it's non-absorbed light, and we only have that is scattering. Then what happens here is described by the Maya theory, that the particles interact in two main ways. One, the particle can absorb, and when it absorbs, transform light energy to heat energy. So this one is really difficult to measure. That's absorption. So it's not really, it's difficult to measure by absorption. So it's easier to measure by scattering. So the particles can scatter light, redirect the energy to a different direction, like you see. And so we can now have an instrument here that will now detect at this point, and then we're able to measure. Next one. So click again. I want all of them to come out. So the light source comes, and then here we're supposed to have the particle that the light will pass, and it will hit it. And what I showed you before, the light ray is diffracted, and it goes there to the detector, and you have this. So that makes it easy for the light scattering to be used for detecting for a particular particle. So let's go on. So now we're talking of a particular particle, that happening to it. So now, how much light would a particle scatter? If the particle could scatter light, how much light would it scatter? So now, in this case, we're interested in the scattered light intensity. How much of it will it scatter for the measurement if the light hits that particle? And so it's still this Maya theory that we use. And so this is the scattered light intensity. So to calculate and know how much is scattered, this is a formula you use. We have Maya intensity parameters here, and then you have the incident intensity and the wavelength. And so the distance between the particles and so on. So with this, you can calculate and know how much scattered intensity light, how much light scattered we have. Next one. So the nephelometers, in this case, the principle of operation here are the optical devices that indirectly report mass concentration. They indirectly report mass concentration. So the amount of time that light is scattered away from the photodiode is proportional to the mass of the PMs. So for 1 PM, for one particular matter, it will just scatter once. For as many as the dust particles, it will now replicate as many scatterings. And so this helps to know how much, as many as scattered, it's proportional to the mass of how much PM comes in. So, and so this cannot distinguish particles at less than 300 nanometer or greater than 3 microns. So that's a little limitation. And also ambient humidity also causes some limitations also in reporting PM 2.5 mass using this method or this kind of sensors. Next slide. So when the light is here, this is how it works. The laser light comes in, and then Yeah. So it hits where you have your can you let me see this? So the light source is here, and then the air channel that brings in the air, the dust, and all those, and then the light scattering happens there. And so that scattering is recorded. You'll have the electrical signal, and many times it could be very, very low concentration, and so you will need filter and amplifier circuit so that to amplify the signal for you, for it to be processed, and then you now have the final result out there. And you move it. So talking about sensor sensitivity, there are a lot of factors that affect sensor sensitivity. You have the shape of the particle, the size of the particle, the composition of the particle, and humidity. I mentioned before that we do passive and active sampling. Those PMs can carry metal, can carry organics, can carry different kinds of pollutants. So the composition of the PM will also affect the sensitivity of the sensor, just like the other ones. And also how much loaded dust, how much of it is going in also affect the sensitivity, and also how old the sensor is. Sometimes one needs to change the sensors when they're old. Next slide. So for the optical particle counter, it also operates just like the nephelometer, except that this one uses mirror. It uses a mirror here to reflect what is happening at the other side. So that's it with that. I think in the question time, we'll also look at that more. But this one is very good because it can cover from 0.3 micrometers to 40 microns. And this is very good for us. So it's good if one has a sensor that has a combination of this and the other one. Next slide. So a sensor like Quant AQ has a combination of the two to be able to capture both the PM 2.5, which falls within what I showed you before, and PM 10, which can be captured by the optical particle counter. And both the nephelometer and this other one, combination of it, so you can capture at all sizes. So this does that combination. Next slide. I'm trying to rush so that I can capture and touch everything I have here. So reference monitors. Reference monitors, they are not low-cost monitors. So these are the ones that comply with standard protocols for quality assurance and quality control. We have examples of the US EPA that establishes the protocol for monitoring criteria air pollutants. I remember Dan talked about criteria air pollutant. So the 40 CFR, that's the Code of Federal Regulations. It's one of those such protocols, and then regulate the federal reference monitors. Those are the reference monitors. Can either call it Federal Reference Monitor, FRM, or Federal Equivalent Monitor, or Research Grade Monitors. That's the same thing. Can you move it? So I now come to what is available. Right now in Lagos, thanks to though I cannot pronounce it very well. Affluence, thanks to Osu Effluve in France, the university, with Afri-Air, donated 2 reference monitors to us recently in 2023, around September, thereabouts. We received the EQ-Sync, which is a reference monitor for gaseous pollutants like the ozone and the NO2. And late December also, we received the feeders here, which is a reference monitor for PM 2.5, PM 10. And then also we are expecting the BAM, which is coming as a result of the project that is funded for us by the United States Department of State, US DOS, a particular project that I'll still talk of as we go on, that BAM. So we're yet to get that, but we've already paid for it. So these are what we have. Presently, without this, there is no reference monitor in Nigeria, except one that we have in US Embassy in Lagos and another one in US Embassy in Abuja. So it's been a very difficult thing for us. Even the World Bank project that was carried out was not, the devices could not be validated because we did not have reference monitors. So we're very grateful to the donors for this. So now in Nigeria, I have many of my Nigerian people here. So you have your local sensors. Right now, these are being set up in the University of Lagos. So you can come in and co-locate your sensors for calibration and validation. Next slide. So how reference monitors work by gravimetric. So, and it's a 1 hour time resolution. So using a microbalance, detects the change in frequency of oscillation of a cantilevered glass tube. So small vibrating glass tube whose oscillation frequency changes when aerosol particles are deposited on it, it increases its inertia. So if you have one particle going in, the oscillation, the frequency is low. When you have much more the particles, the more the frequency of the oscillation, the more it changes. And so and that is how it is it's measuring the concentrations or the mass of the particulates through change in oscillation frequency from what it was, and the final one subtracting what it was. So that difference is equal to the mass of whatever went in there and caused the oscillation. This next slide. So this is what I'm just talking about here, the frequency here, and then the spring rate and the mass. So to get the mass, you need to know the rate, the spring rate, that's the oscillation, the frequency. So, and then the initial frequency subtracted from the original one. From there, you can compute and then obtain the mass of what particulates got in there.